So let me hear from your groups, first of all, a complete set of eigendata for these four matrices. So let's start with the matrix A. So what were the eigenvalues that you found for matrix A? The eigenvalues.
Values, 1 and 1.
1 and
1.
1. So you found...
Oh, no, sorry. It should be 3 right now.
3?
Sorry, I'm getting confused with that ending. Yeah, 3.
3 and 1?
No, there's no 1, just 3.
Oh, just 3? Okay. And what was the basis you found for that eigenspace?
1, 1.
1, 1. Gotcha. Okay. How about the matrix B? Other group.
7 and 3.
7 and 3. What was the basis for the eigenspace of 7?
1/3 and
1/3,
1.
1, okay. And for the eigenspace of 3?
7 and -1.
7, -1. Okay. There we go. So already here, we're seeing a difference between these two matrices. Namely, the first matrix ended up having only a single eigenvalue, or at least a single eigenvalue that you could sort of make a prediction based on what you were seeing in the app. 1 eigenvalue. Whereas the second matrix had 2 eigenvalues.
Oh, sorry, the basis for the second one is -1 and 1. Or I don't know.
Oh yeah, -1 is very easy to look like a 7, so that's fine, we'll fix that. Like this?
-1.
-1, 1?
I don't know.
It actually describes the same
Yeah,
subspace, so it doesn't matter whether we use 1, -1, or -1, 1. It's the basis of the same thing. But our first matrix here had 1 eigenvalue, and the second matrix had 2 eigenvalues. What about C? How many eigenvalues did it have? Let's just do that the quick way.
How many values?
How many eigenvalues?
1.
1. And what was it?
2.
Lambda equals 2. And matrix D? What were its eigenvalues?
7 and -1.
7 and -1.
And then if the eigenvalue 7, the basis is -1/2 and 1.
-1/2, 1 for the eigenvector, okay.
And then the other eigenvector. Is that the basis of the
That's the basis. We would call it, well, it is an eigenvector, but it's also a basis for the eigenspace.
Then the next one's 3/2.
3/2, 2.
No,
Okay.
3/2, 1.
3/2, 1. Okay. All right. So sneakily, I managed to give one group both examples that have only a single eigenvalue, and the other group got both examples where we had a pair of eigenvalues. But I wanted to lead the way that we led today, because this process of discovering a basis for the eigenspace, this is the complicated part of eigenanalysis, eigenvector eigenvalue analysis. It's the end game. But really, in order to do it, we need to know, or at least we need to have a suspicion on what the eigenvalues are in the first place. So a complete picture of eigenvector eigenvalue analysis has to begin with us determining those eigenvalues somehow. Without the eigenvalues, we can do nothing. We have to know the eigenvalues first before we can determine the eigenvectors, i.e. a basis for the eigenspace. So our next question is, how do we determine eigenvalues? And how can we tell, for instance, when a matrix has a single eigenvalue versus when it has 2 eigenvalues? Is it possible for a matrix to have no eigenvalues? How many eigenvalues might a matrix have? So that's the next question.
Is it because of the zeros?
It had something probably to do with those zeros. So let's actually take that A matrix that you were working on a minute ago. And let's use that as the example that we'll hang on to for a few minutes here. What was your A matrix again?
3, 0, 2, 1.
3, 0, 2, 1. So we'll crank this up to 3, turn that down to 0. So what was that? 3, 0, 2, 1? All right. So hunt around with this a little bit, and we find out that, so there's a vector that looks like it's getting stretched by this matrix A. If we crank up the annotation a little bit, we can see that it's being stretched by approximately a factor of 3. So there was your eigenvalue of 3 that you found. And if I move this around a little more, I think there's an eigenvalue that you might have missed. How about right there? It looks like this vector is being stretched to 1 times itself. So I believe that this matrix actually has that second eigenvalue, the eigenvalue of 1 in addition.
So it would just be itself.
That's right. So in this example, x, the vector x, which in our example looks like it's probably 0, 1 or something like that, but whatever it is, when we multiply it by this matrix A, we're getting 1 times itself. So maybe the question we can ask ourselves is, well, how come we didn't see that coming? How could we take this 2 by 2 matrix and determine what its eigenvalues are algebraically instead of relying on the graphical and numerical evidence that we have coming from this app? So let's go back to where eigenspaces come from in the first place. As we were saying before, an eigenspace is really just a solution set to the eigenvalue-eigenvector equation. And the eigenvalue-eigenvector equation is AX equals lambda x. Where lambda here is a scalar. And to find this solution set, we took the eigenvalue-eigenvector equation, we subtracted lambda x from both sides. And then on the right-hand side, we ended up with a 0 vector. And on the left-hand side, when we factor the x out, the relevant matrix that makes up our matrix vector equation now is A minus lambda times the identity. So this is the equivalence that we have again. The eigenvalue-eigenvector equation that we're really interested in solving is equivalent to the matrix vector equation. A minus lambda I times x is equal to 0. And again, what do we want? We want solutions to this equation, because this is always consistent, remember, because the 0 vector always works. We'll always satisfy this equation no matter what. But what we want is non-trivial solutions, so that we can get interesting eigenvectors that aren't just the 0 vector, non-trivial solutions. But, and this is what Zach and I were talking about a little bit during this activity, if we want non-trivial solutions to this system of equations, what does that tell us about the matrix A minus lambda times the identity?
Linearly dependent.
Yeah, so it begins with the observation that we must have a free variable. And we have a free variable exactly when the columns of A are not independent. It has dependent columns. So that we get a free variable. But we're only doing eigenanalysis on square matrices. We're never doing it with rectangular matrices because we need the image, we need the vector AX to live in the same vector space as the vector X does. So we need our matrix to be square. So if I have a square matrix that has dependent columns, Zach, what were you and I saying about this matrix? If a matrix has linearly dependent columns, what else do we know about it? It has a free variable, and so it has non-trivial solutions to the homogeneous equation. The solution to the homogeneous equation is not unique.
Yeah.
But those are all statements about its columns. We can also think about the rows. If it has dependent columns and it's square, that means that one of its rows is missing a pivot also. So it has dependent rows. Pulling all of that information together, what is this matrix? Maybe it's easier to ask this question. What is this matrix not? It's not invertible. Because remember, the invertibility of a square matrix is equivalent to the linear independence of its columns. So if we have dependent columns, we have a matrix that is not invertible. And this is the key observation that is going to start us down a path that will allow us to find eigenvalues, is that what we want is we want A minus lambda I to be not invertible, which is all well and good. That's a linear algebra statement. How do we turn that linear algebra statement into a plain old algebra statement? In other words, I want to come up with an equivalent condition to this that will allow me to determine something that I can solve that will determine my eigenvalues. lambda. What's my intermediate step? Why does this section on eigenvalues and eigenvectors come in Chapter 5 instead of in Chapter 2? What additional tool do we have that can tell us whether a matrix is invertible? The span of the columns has to be the entirety of Rn. That's true. Sorry, actually we want it not to be the entirety of Rn because we want this to be dependent, the columns to be dependent. But that's not a very easy criteria that can let us solve for lambda. That's a Chapter 4 thing. We might need a Chapter 3 thing. What is the determinant of a matrix that is not invertible? 0. And that is the intermediate step. That's the keys to the kingdom here. A minus lambda I is not invertible precisely when its determinant is equal to 0. And that equation is the equation that we can solve to determine the eigenvalues of a matrix. So if I can solve this equation, determinant of A minus lambda times the identity is equal to 0, then its solutions will be those values of lambda for which A minus lambda I is not invertible, and therefore A minus lambda I has dependent columns, and therefore this matrix equation has non-trivial solutions, and therefore the eigenvalue-eigenvector equation has non-trivial solutions. So it all hangs on that.
The determinant of that, and when you get 0, that means it's not invertible, which means that you have dependent columns and rows, which leads to you having more than one eigenvalue.
Leads to you having more than one solution to the eigenvalue-eigenvector equation. In other words, we have a non-trivial eigenvector, which is what we want.
Okay.
So finding the lambdas will tell us which eigenvalue-eigenvector equations can have non-trivial solutions. So let's follow that through with this example. If we don't know what lambda is, we're just going to leave it as lambda. So I'm going to subtract lambda times the identity from my matrix A. And what I'm going to get is on the diagonal 3 minus lambda, and on the other diagonal entry is going to be 1 minus lambda, and then my off-diagonal entries remain the same. And so this matrix here is A minus lambda times the identity. And now according to this equation down here at the bottom, which for the sake of adding in additional terminology is called the characteristic equation for the matrix A. Characteristic being a synonym for the German prefix eigen, by the way. That's what eigen stands for. So now, according to that equation, I'm supposed to take the determinant of this matrix and set it equal to 0. Now, what do I get when I take the determinant of this A minus lambda I? Since we have a 2 by 2 matrix, this determinant is not particularly onerous.
You multiply 3 minus lambda and 1 minus lambda minus 2 times 0.
Minus 2 times 0. There we go. And then I'm supposed to, in order to determine the eigenvalues, set this equal to 0 and solve for lambda. So let's finish the arithmetic, the algebra on the left-hand side. We'll end up with, well, I'm going to leave it factored actually. 3 minus lambda, 1 minus lambda, because I also have here minus 0 is equal to 0. And since I left it factored, the amount of additional work I have to do here is pretty minimal. 3 minus lambda is equal to 0 on the one hand, 1 minus lambda is equal to 0 on the other hand. So in the first case, lambda equals 3, and in the second case, lambda equals 1. And there's our eigenvalues. And that's all there is to it. Set up the characteristic equation, solve the characteristic equation. And that will tell you algebraically what your eigenvalues are. And before we move off this topic and go back into, getting some more practice with doing this, I have to ask you, what kind of an equation are we getting here? in this example, we're getting a quadratic equation, right? It's a polynomial of degree 2. And why is it a polynomial of degree 2? Back up to this matrix. How could we have known that when I find the determinant of this matrix, I'm going to get a quadratic polynomial? Because we're multiplying down the diagonal, which is the only place that we have lambdas. And how many diagonal entries do we have? 2, because we have a 2 by 2 matrix. So that's a connection.
Is there an easier way to find the lambdas if it was like...
I'm glad you asked that question. Yes and no. Because the characteristic equation involves a determinant, generally, actually churning out the characteristic equation by taking the determinant of a minus lambda times the identity is sometimes obnoxious. There's really not a good way to get around taking that determinant. The good news is I suppose you could use whatever method for that determinant that you like, whether it be cofactors or whether it be row reduction or whatever. But really, there's also something called the method of ascending minors that is essentially just kind of a backdoor way of using the cofactor method for that determinant as well. That's in one of the videos. I don't have a lot of practice using that method. Usually I just crank out my own cofactor expansion for the determinant by hand. But at least for the 2 by 2 case, it seems pretty painless. And 3 by 3 even is not too terribly difficult. So, given that a 2 by 2 matrix produces a quadratic characteristic equation, what do you think is the general example for an n by n matrix? What is the characteristic equation going to look like? Maybe let's just set up a single imaginary example. So here's a 6 by 6 matrix. Let's suppose that I were to take this matrix minus lambda times the identity. Then what would that look like? I would just subtract lambda from every one of the entries on the diagonal. And so in this case, I would get negative 2 minus lambda on the diagonal, followed by 9 minus lambda on the diagonal, followed by negative 12 minus lambda on the diagonal, 10 minus lambda. Sorry, this is 5 by 5, not 6 by 6. My eyes are deceiving me here. 10 minus lambda, and then 0 minus lambda. And then all the other entries in this matrix would remain the same as they were. So 0, 8, 1, 11, 0, 1, 2, 2, 0, 0, 8, 18, 0, 0, 0, 3, and 0, 0, 0, 0. So here's a minus lambda times the identity. Now what is it about this matrix that makes finding its determinant relatively easy?
You just multiply down the diagonal?
Yeah, you can just multiply down the diagonal. Because it's triangular, all of these entries here are 0. So actually, a cofactor expansion can persuade us that multiplying down the diagonal is okay. Because if we were to expand, let's say, along the first column, then our first cofactor product would be negative 2 minus lambda times the determinant of this thing, plus 0 times the determinant of something else, plus 0 times the determinant of something else, etc., etc. But the determinant of that big 4 by 4, if we expand it down its first column, if we expand that down its first column, is going to be 9 minus lambda times the determinant of this 3 by 3, plus 0 times the determinant of the next minor, plus 0 times the determinant of the next minor. And then the determinant of this 3 by 3, you get the picture. Negative 12 minus lambda times the determinant of this 2 by 2, plus 0 times something, plus 0 times something. And then the determinant of this 2 by 2 is the product on its diagonal minus 3 times 0. Okay. So when all of that dust settles, don't know why this little purple line is still in there. Go away. When all that dust settles, this determinant is just the product on the diagonal. That works for any triangular matrix, by the way. Any matrix which has only zeros below its diagonal or only zeros above its diagonal. The determinant is just the product of all the entries on the diagonal. And so here we're going to have negative 2 minus lambda times 9 minus lambda times negative 12 minus lambda times 10 minus lambda times negative lambda. And
there's a 0 on the diagonal that just says determinant 0.
Yeah, but the thing is, in our characteristic equation, yeah, there was a 0 on the diagonal.
Since you're not you're multiplying or subtracting it.
Right.
But I was just wondering about the determinant of that
Hmm.
first. Because you could take it by just the diagonal of that too. So
The diagonal of
A.
A? Well, yeah. So actually, let's make that connection really quickly too. The determinant of our original matrix, because it was a diagonal matrix, as you say, the determinant of our original matrix was 0. Now, what are the eigenvalues? According to the solutions of this characteristic equation, we can read them right off, actually, because this is already factored.
2, 9,
So negative 2, 9, negative 12, 10, and then the last one is 0. So one of the connections that we're going to forge over the next few classes is what is the connection between the eigenvalues of a matrix and the determinant of that matrix? Is it true that a matrix whose determinant is 0 will always have an eigenvalue of 0? Maybe. But at least in this example it seems to be true. If we were to multiply out this polynomial, what degree would it have? 5th degree. So it's a quintic. Equation. And that's generally true for any n by n matrix. So going back to the question we were seeking to answer here, any n by n matrix so the conclusion of this is if A is an n by n matrix, then the characteristic equation for A is going to be a degree n polynomial equation. And the big finish here is how many solutions can a degree n polynomial equation have? It can have at most n distinct solutions. That's the fundamental theorem of algebra. So the reason that a square matrix can have only a finite number of different eigenvalues, so there's only a finite number of different lambdas that can make the eigenvalue-eigenvector equation have a non-trivial solution. The reason is the characteristic polynomial is a polynomial of degree n, where n is the row or column dimension of our matrix. And therefore, because degree n polynomials can only have up to n distinct solutions, an n by n matrix can have only up to n distinct eigenvalues.
So